So here we are, maybe looking back at the Earth from outer space. And often in textbooks you see the moon is drawn quite close to the Earth. Well, this is something which isn't actually true. If the moon was really this close to the Earth, then every time it got to night time, you see that pretty much most of the sky was covered by the moon. In actual fact, the moon is a lot further away, and it's really off the map actually. But I'll put it over here for scale. Now the other thing is around the Earth there are these various satellites moving around. So here we have a satellite, again obviously not to scale, but these satellites again are often drawn in pictures orbiting quite far away from the Earth. In actual fact, the artificial satellites that we have in just above the Earth's surface are pretty much skimming the Earth's atmosphere. And if we were to maybe try and place on one of these satellites onto this diagram here, we'd actually find that the satellite is pretty much next to the Earth. Okay, it's hardly any separation at all. And what I'd like to look at now is the strength of the gravitational field strength as we move away from the Earth out towards the moon and maybe beyond that. And this is basically something that's quite important because, you know, the reason that the moon keeps going around the Earth is because there's a massive gravitational attraction that keeps it in orbit. But people think that when you have maybe a spaceman or an astronaut up on maybe the International Space Station that they're weightless. Well, this isn't the case. The weight of an astronaut on the space station or on the International Space Station is pretty much identical to their weight on Earth. And really, they're not actually weightless. So why is that? Well, let me show you. So on the Earth's surface, the strength of G is equal to 9.81 newtons per kilogram. But we can maybe try and work out what is the strength of G perhaps over here or over here, or in actual fact anywhere radially away from the Earth. And there's a couple of equations that we can use. First of all, we know that G is equal to F over m. So this is the force per unit mass. But we've also seen from Newton's law of gravitation now that the F is equal to minus gmm over r squared. And basically this is the size of the force and it's related to the mass, so we'll call big M the mass of the Earth, and also the mass of the object around it. So basically what we can do is we can substitute this F back into this equation over here to say that G is equal to minus gmm over mr squared. What we can then do is we can cancel the m's to say that at any point around this object, this sort of radially around this object here, G is equal